So you asked about section 5.1 on inner products, number 4, and C01 is a vector space. So this is a set of all real valued functions from the unit interval to the real line, which are continuous. And on this space, there's an inner product. So the inner product of two functions, f and g, is defined to be the integral from 0 to 1 of f of t, g of t, dt. So we have, for example, the function f of t equal to 1 plus 2t. So this is the inner product, and the length of a vector is just the inner product of the vector with itself, and you take the square root of that. So here, this is our vector, this function. So what is the inner product of f with f? It's the integral from 0 to 1 of f of t times f of t. That's just 1 plus 2t squared dt. Right, so that's the first step. All right, this is the inner product of f times f. 1 plus 2t times 1 plus 2t is 1 plus 2t squared. So that's the integral from 0 to 1, 1 plus 4t plus 4t squared. And then you integrate this, you get 1. Right, I mean, this is the integral of 1, which is 1. The integral of 4t, which is 2t squared from 0 to 1, is 2. Well, let me just write it all out. So this is the integral from 0 to 1 of 1 dt, plus the integral from 0 to 1 of 4t dt, plus the integral from 0 to 1 of 4t squared dt. The integral of 1 is 1. The integral of 4t is 2t squared. We're evaluating from 0 to 1. The integral of 4t squared is 4/3 t cubed from 0 to 1. So this is 1 plus 2 plus 4/3. So that's, I believe, 13/3. So the length of this vector v is the square root of 13 over 3. So these are just exercises in calculus. The function g of t is e to the t. So the inner product of g with itself is the integral from 0 to 1 of e to the t times e to the t, which is the integral from 0 to 1 of e to the 2t dt. The integral of e to the 2t is 1/2 e to the t, e to the 2t, from 0 to 1. That's 1/2 e squared minus 1. So the length of g is the square root of 1/2 e squared minus 1, and so on. And again, it's just the integral of h is you're integrating the cosine squared. So you might have to go back. I'm sorry, is there a question?
Yes.
Go ahead.
Can you explain where it says in parentheses f and f equals that line?
Yeah. So the inner product of two functions in this vector space is the integral of their product. So the integral of f and f, of f with f, is the integral from 0 to 1 of f of t times f of t dt, which is the integral from 0 to 1 of f squared of t dt. F of t is 1 plus 2t. So this is the integral from 0 to 1 of 1 plus 2t squared.
So f to the second power is 1 plus 2t.
No, f of t, this is, the book says, this is f of t is the function 1 plus 2t. If you multiply 1 plus 2t by itself, you get 1 plus 2t squared, right?
Okay, understand. Thank you.
When we want, we're given f of t is 1 plus 2t, g of t is e to the t. So the inner product of f and g is the integral from 0 to 1. This is the definition, f of t, g of t, dt. This is the integral from 0 to 1 plus 2t, e to the t, dt. You have to integrate this, right? So you can integrate by parts, 1 plus 2t, 2, e to the t, e to the t. So this is the same as 1 plus 2t, e to the t, evaluated from 0 to 1, minus the integral from 0 to 1 of 2e to the t dt. That's, what is 1 plus 2t e to the t from 1 to 0? So this is, when t is 1, you get 3e, and when t is 0, you get 1. And what is the integral of 2e to the t? It's 2e to the t evaluated from 0 to 1. So this is 3e minus 1 minus 2e minus 2. So if I did my arithmetic correctly, this is e plus 1. But again, you just have to check the integration. But this is the definition of the inner product in this vector space. So you're integrating the product of these two functions. Right. I mean, these are just exercises in integration. And, you know, sometimes in math classes, when there's a prerequisite, you actually need to know the material in the prerequisite classes. But that's, right? I mean, are there any, do you have other questions about this problem? And there are other parts that you would like me to do? Or other problems I should try to do?
Could you do 5?
Okay. So in problem 5, we have a vector space and a function from V cross V into R. So to say it's bilinear means so this is for every pair of vectors V and W, f of VW is some real number for all pairs of vectors V and V and W and V. To say it's bilinear means that if you fix W and you look at f of, let's say, C1V1 plus C2V2, comma W, so this is some linear combination of vectors in V. This will be C1 f of V1W plus C2 f of V2W. It's just like saying for fixed W, this is a linear transformation of the vectors in the first variable. And similarly, if you fix V, f of V times some linear combination, C1W1 plus C2W2, that's C1 f of VW1 plus C2 f of VW2. So that's just the definition of bilinear. An inner product is bilinear but it's also symmetric and positive definite. This is bilinear. So f of 0v, you can write, well, 0 is the same as 0 plus 0, comma v, right? So 0 equals 0 plus 0, but using the bilinearity, this is f of 0v plus f of 0v. So if you subtract f of 0v from both sides, you get 0 equals f of 0v. That's what you wanted to prove. And it's exactly the same thing if you put the 0 in the second coordinates. And f of minus v comma w is f of minus 1 times v comma w. And again, by the bilinearity, you can take the scalar outside. This is minus 1 or minus f of vw. That's, half of part 2, and the other half is just the same kind of argument with w instead of v. Let me do number 6, because it's in the same spirit, like this. So we have an inner product space V and a vector W in V. And so we let S be the set consisting of just this vector W. So we define S with a perpendicular sign. We usually read this as S perp. This is all vectors in V which are perpendicular to W. So for example, in the plane, if this were the vector W, everything perpendicular to W would be on this line. So this would be my S perp. This is a perpendicular line through the origin, which is a one-dimensional subspace, and we want to show that in general, S perp is a subspace. So you just have to show that S perp contains 0, is closed under vector addition, and is closed under scalar multiplication. So first of all, the inner product of 0 with any vector is 0. So the 0 vector is in S perp. And if V1 and V2 are in S perp, that means the inner product of V1 and W is 0, and the inner product of V2 and W is 0. But then V1 plus V2, inner product with W, by the bilinearity, this is just the sum of the two separate inner products. 0 plus 0 is 0. And if V is in S perp and C is a scalar, the inner product of CV and W is C times the inner product of V and W. And that's C times 0, which is 0. So and then this is part A. So this proves that in an inner product space, if you fix any vector and you look at everything perpendicular to that vector, that forms a subspace. And part 2, this is part 1, is to prove S perp is the whole space if and only if the vector W is the 0 vector. So let's see. Well, the first part is easy. If W is the 0 vector, the inner product of V with W, which is the inner product of V with 0, is 0 for all V in the vector space. So S perp is all of V. On the other hand, if S perp is all of V, then W is in V. So W is in S perp. So the inner product of W with itself is 0. And the only time the inner product of vector with itself is 0 is if the vector is 0. So the only time you get this perpendicular space S perp to be everything is when your vector W is 0. Okay. Any other questions you would like me to do? So let's just recall. We have an inner product space. If V is any vector, the length of V is defined to be the square root of the length of the vector with itself. And again, this corresponds with your basic understanding of the length of a vector. So suppose we're in R2 with the inner product x1, y1, inner product with x2, y2 is just x1, x2 plus y1, y2. Right? So if you have the vector xy, that's my vector v. What's the length of v? It's the square root of the inner product of v with itself. The inner product of xy with itself is the square root of x times s plus y times y. That's square root of x squared plus y squared. Right? That's just the Pythagorean theorem. You have a right triangle with sides x and y. The hypotenuse has length square root of x squared plus y squared. So, and in Rn, with the standard basis, E1, E2 up to En, where E sub j is the vector whose coordinates are all 0, but a single 1, and then everything's 0, in the jth place. This is the jth coordinate. So that's the standard basis vector Ej, or I could write Ej in terms of the Kronecker delta, delta 1j, delta 2j, down to delta nj, where the Kronecker delta, which is a very important function in linear algebra and elsewhere, the Kronecker delta, delta ij is defined to be 1 if I equals j, and 0 if I is different from j. Right? So in R2, E1, which is 1, 0, is the vector in terms of the Kronecker delta, delta 1, 1, delta 2, 1. And E2, which is 0, 1, is delta 1, 2, delta 2, 2. Where the coordinates, where the subscripts are the same, you get a 1. Where they're different, you get a 0. Then we say a unit vector is simply a vector with unit length. That is, the vector is v, the length of the vector is 1. That's a unit vector. And a set S of vectors is orthogonal if the inner product of any two vectors is 0 for vi different from vj in S. So you're the set of vectors and any pair of them is orthogonal, right? Remember, orthogonal is just another word for perpendicular. And two vectors are orthogonal or perpendicular if their inner product is 0. So in R3, three-dimensional space, if this is the unit vector E1, the standard basis vector, here's E2, 0, 1, 0. Here in the z-axis direction is E3, which is 0, 0, 1. The set S, consisting of these three vectors, E1, E2, E3, is orthogonal. Because any pair of them is perpendicular. The vectors in any pair is perpendicular. The set S is called orthonormal if S is orthogonal. If it's every pair of vectors in S is perpendicular and every vector in S has length 1, is a unit vector. So this set is not only orthogonal, I can actually say this set is orthonormal because each of these vectors has length 1. One very nice thing about orthogonal vectors is that they are linearly independent. So this is a lemma. This is lemma 5.2 on page 280. It says every set of orthogonal vectors is linearly independent. These are all non-zero vectors. So, proof that S be an orthogonal set of vectors, that V1, V2 up to Vk be a subset of S. And suppose some linear combination of these vectors is 0. I have to show that C1, C2, all of these scalars are 0. And I can do that using the fact that these vectors are orthogonal. So if I, just to make the notation more concise, using sigma notation, this is summation Cj Vj j goes from 1 up to n. So suppose I take vi, that vector vi, which is one of the vectors in this set, and I take its inner product with summation cj vj. J goes from, goes from 1 up to k. Cj vk. Right. On the one hand, this is just the inner product of vi with the 0 vector, because this is 0, so this is 0. So this inner product gives me the number, the scalar 0. On the other hand, by bilinearity, this is summation, j goes from 1 up to k, cj, inner product of vi and vj. Sorry, yeah, all right, that's okay. And what is this? Well, vi, vj, that inner product is 0 for all I different from j. That's what it means for this set to be orthogonal. So if I is different from j, this is 0. So this is summation for all j going from 1 up to k, with j different from I, cj times 0. Plus, I get the term when j is equal to I, ci, inner product of vi with vi. So this is just 0. And this is ci, the length of vi squared. And again, that's equal to 0. But vi is not the 0 vector. So its length has to be positive. It can't be 0. So c sub I equals 0. And this is for all I. So if you have an orthogonal set of vectors, it's linearly independent. Now, what's very nice is when you have a basis that consists of orthonormal vectors. So suppose V is an inner product space. And script E, consisting of, let's say it's n-dimensional, is an orthonormal basis. For V. So what does orthonormal means? It means that the inner product of EI and EJ is 0 if I is different from J. And if I equals J, that's just the length of this vector. And if the vector is also an orthonormal, these are unit vectors. Every vector has length 1. So another way of saying this is the inner product of EI and EJ is the Kronecker delta. It's 1 when I equals J and 0 otherwise. So let V be any vector in V, and let V with respect to E, this is the coordinate vector for V, vector V, with respect to the basis E. That means that if you write V as some linear combination, then the coordinate vector for V with respect to E is the column vector x1, x2 up to xn. But what's very nice about an orthonormal basis is if you have two vectors, say V is this linear combination summation xi ei, I goes from 1 up to n, and W is another vector, y1 e1, y2 e2, up to yn en, which I can write as summation, say yj ej, j goes from 1 up to n. The inner product, which might be very complicated, becomes very simple when you write vectors with respect to an orthonormal basis. Because then what is the inner product of V and W? This is the inner product of summation xi ei, I goes from 1 up to n, comma, summation j goes from 1 up to n, yj ej. If we expand this using bilinearity, first, this first term, when you expand, you get summation I goes from 1 up to n, xi, inner product of xi with this vector in the second coordinate. And then when you expand this by bilinearity, you get summation I goes from 1 up to n, summation j goes from 1 up to n, xi, yj, inner product of ei and ej. This is this double sum. I goes from 1 to n, j goes from 1 to n, xi, yj, and the inner product of ei and ej is the delta, the Kronecker delta, delta ij. This is 0 except when I equals j. So this becomes summation xi, yi, I goes from 1 up to n. And this is the standard inner product. So when you have an orthonormal basis and you write your vectors as linear combinations of the vectors in the orthonormal basis, and you look at the coordinate vectors, the inner product of V and W is just the standard inner product. Standard inner product. So orthonormal bases are nice, but you're not always given an orthonormal basis for a vector space. So we have the following problem. Given a basis for an inner product space is just a vector space where we've defined an inner product. Construct from it an orthonormal basis. Of course, it's enough to start with an orthogonal basis. So given an orthogonal basis, that just means every vector is perpendicular to every other vector, but they don't necessarily have unit length. You take V1 up to Vn, orthogonal. So the inner product of Vi, Vj is 0 for I different from j. And each vector Vi is different from 0. So the length of the vector Vi is some positive number. And suppose I define a new vector, E sub I, to be 1 over the length of the vector Vi times the vector Vi. So this is a vector that is of length 1. This is a unit vector. Because the length of this is just, is 1. And the inner product of any Ei and Ej is going to be 1 over the length of VI times VI, 1 over the length of VJ times VJ. I can factor these scalars outside of the inner product sign. This is 1 over the length of VI, 1 over the length of VJ, times the inner product of VI and VJ. And this is 0 if I is different from J. So given an orthogonal basis, you can easily construct an orthonormal basis, but by dividing each vector in the basis by its length. So there is a nice way to construct an orthonormal basis from a basis, and it uses the following simple piece of geometry. So suppose we have, let's suppose we have the vector W, and we have another vector V. What I would like to do is decompose V as a sum of two pieces. One is parallel to W, and the other is perpendicular to W. So given W, some non-zero vector, and V, let's say a non-zero vector, otherwise there's nothing interesting to do. You want to find a vector, you want to write V as a sum of two vectors, V1 plus V2, where V1 is parallel to W. What does it mean for one vector to be parallel to another? V1 is just some scalar multiple of the other. And V2, you want to be perpendicular to W. So the inner product of V1 and V2 is 0. So we have the following problem in geometry. Given a vector W and a vector V, I want to decompose V into a sum of two vectors, one parallel to W and one perpendicular to W. And I claim this can be done, and the solution is in fact unique. There's only one way to do it. So let me draw this picture again. Well, there's the picture. Suppose I let V1 be a certain scalar multiple of W. And that scalar multiple will be the inner product of V and W divided by the length of W squared. So this is some scalar times W. So this is parallel to W because it's a scalar multiple of W. And I want to let V2 be equal to V minus V1. Now, of course, if I do this, then V equals V1 plus V2. And I claim V2 is perpendicular to W. So I have V as V1 plus V2. V1 is parallel to W, and I'm going to show this is perpendicular to W. So to say that V2 is perpendicular to W, means that the inner product of V2 and W is 0. So that's what I have to compute. What is the inner product of V2 with W? Well, V2 is V minus V1, that inner product with W. So this is by linearity or bilinearity, the inner product of V with W minus the inner product of V1 with W. This is V1. This is the inner product of V and W minus the inner product of V1, which is the inner product of V with W over the length of W squared, W, comma, W. This is a scalar. I can take that outside of the inner product sign. So this is VW minus VW over the length of W squared. That was this constant. Times the inner product of W with W. But the inner product of W, a vector with itself, this is just the length of W squared. So this cancels this. I get VW minus VW, which is 0. So V2 is perpendicular to W. So I now have at least one way to write V as a vector parallel to W and a vector perpendicular to W. So suppose we have another representation of V as V1 prime plus V2 prime, where V1 prime is parallel to W and V2 prime is perpendicular to W. I must show V1 equals V1 prime, V2 equals V2 prime. So it's unique. So what do I have? I have on the one hand, V is V1 plus V2 by the method I just showed, I worked out. And we have some other way to write V is V1 prime plus V2 prime. So V1 and V1 prime are both parallel to W. V2 and V2 prime are both perpendicular to W. What does this say? This says that V1 minus V1 prime equals V2 prime minus V2. So this is a vector. Let me call it V1 tilde. And this vector I'll call V2 tilde. Actually, it's the same thing. Let me just call this vector V tilde. So what can I say about V tilde? These two vectors are parallel to W, so the difference is, so V tilde is parallel to W, and at the same time, it's also perpendicular to W. So on the one hand, V tilde inner product with W is parallel to W, so it's some scalar multiple of W. On the other hand, it's perpendicular to W. Let's see. Make it easier. So V tilde is parallel to W. So V tilde is some scalar multiple T times W. On the other hand, V tilde is perpendicular to W. So 0 is the inner product of V tilde and W. but v tilde is tw, so this is tw comma w. This is t times ww. That's t times the length of w squared. W is not a zero vector, the length is positive, so t has to equal 0, which means v tilde has to equal 0, which means v1 equals v1 prime and v2 equals v2 prime. So this is, again, a lemma in the text, and so there's always a unique decomposition. You have a vector w, a vector v, and you can always decompose it into a vector parallel to w, a vector perpendicular to w, and these parallel and perpendicular components are unique. v1 is called the component of v parallel to w. And v2 is the component of v perpendicular to w, or orthogonal, or a third synonym is normal. So there's a unique perpendicular or normal or orthogonal component of any non-zero vector with respect to another in an inner product space. Let's see. Let's look at an example. Suppose I'm in R2 and I take V to be the vector 3, 2, and W to be the vector 7, 3. Let's see, what does that look like? 1, 2, 3, 4, 5, 6, 7. 1, 2, 3. So this is the vector W. And 3, 2 is here. This is the vector V. And I want to find the parallel and the perpendicular components of V with respect to W. So V1 will be this vector parallel to W, and V2 is this vector perpendicular to W. Right? So how do I find them? Let's see. So V1, which is the parallel component, what was the formula that we used? Inner product of V with W over the length of W squared. So this is the inner product of V with W over the length of W squared times W. Here are my two vectors. V is 3, 2. W is 7, 3. The inner product of V and W is 3 times 7 plus 2 times 3. 21 plus 6 is 27. What is the length of W? The length of W squared is the inner product of W with itself. That's the W is the vector 7, 3. This will be 7 times 7 plus 3 times 3. 49 plus 9 is 58. So what we get is V1 is the inner product, 27, divided by the square of the length, 58, times the vector 7, 3. So in terms of coordinates, let's see, what is 7 times 27? That's 189 over 58. And 3 times 27 is 81 over 58. So this is the coordinates of V1. And V2, which is the perpendicular component, is V minus V1. That's 3,2 minus 189 over 58, 81 over 58. So you do the arithmetic, that is, you see, 3 times 58 is 100 and 150, 174. So this should be minus 15 over 58. And 2 times 58 is 116. So this should be 25, 116, 35 over 58. So these are the components of the parallel that's the parallel component, and this is the perpendicular component. So our goal is to figure out a way to construct an orthonormal basis from any given basis in an inner product space. And the idea is based on the following sort of next step. What we just did was, given a vector V, or sorry, what I just done before that's maybe more interesting. Given a vector W and a vector V, we found the component of V in the direction of W and the component of V perpendicular to W. And those were unique. So given one vector W and another vector V, I can find a vector, I can find the component of V perpendicular to W. So I want to extend that technology one step. So again, if you're following on the notes, this is on page 283. Lemma 5.6. So we have an inner product space, a vector space with an inner product, and a subspace W. So here's V, and sitting inside V, we have a subspace W. And suppose W1, W2 up to WK, that this be an orthogonal basis for W. That is, the dimension of W is K, and I have a basis for the subspace W, which is orthogonal. Every pair of vectors is perpendicular. And outside of W, I have a vector W prime. So let W prime be some vector in V, which is not in W. Right? This means W prime is in V, but W prime is not in W. So we already saw that the set of vectors W1 up to WK and W prime is linearly independent. This was actually a problem on the last exam. And I claim, suppose we let W prime be the subspace generated by W and this new vector W prime. So this set is actually a basis for this K plus 1 dimensional space. Call that W prime. So W prime, capital W prime, is the smallest subspace that contains the subspace W and this new vector W prime. And I claim that there exists a vector WK plus 1 and W prime such that the K plus 1 vectors, W1 up to WK, the orthogonal basis for W, together with WK plus 1, is an orthogonal basis for W prime. So suppose we let WK plus 1 be this vector W prime minus, so the component of W prime in the direction of the vector Wi is the inner product of W prime and Wi divided by the length of Wi squared times W sub I. And if I sum this, I going from 1 up to K. So I have this vector W prime, and I'm subtracting from W prime its components in each of the directions of the vectors in the orthogonal basis for W. And I claim that WK plus 1 is orthogonal to all of the vectors in the basis. So orthogonal to Wi, this is 0, equals 0 for all I from 1 up to K. So I have various vectors. Here I have my W prime. I have different vectors Wi, the W1. Here's the component of, there's the component of W prime with respect to W1. You have the component, it's hard to, you have to really understand what's going on to draw the picture, but when you can draw the picture, you see that you have W prime, you have a vector Wi, you have the component of W prime parallel to Wi, you subtract that off, and you do that for all the vectors in the K-dimensional basis, W1 up to WK. And I claim this vector is perpendicular to all the Wi's. So let me kind of draw a picture here. I have a vector Wi. I goes from 1 up to K. I have a vector W prime, and I have, I'll call this the component of W prime in the direction of Wi. That component is the inner product of W prime and Wi divided by the length of Wi squared times Wi. So this is parallel to Wi. And I take W prime and I subtract off the component parallel to WI, and I subtract off all K components, I going from 1 up to K. And I'll call that vector WK plus 1. And I claim that WK plus 1, WJ is 0 for all J from 1 up to K. So this is what I have to prove. So let me do this calculation. WK plus 1 intersect or inner product with WJ. WK plus 1 is W prime minus summation. I goes from 1 up to K. WI over the length of WI squared, WI, comma WJ. This inner product with this. Using the linearity, this is the inner product of W prime and WJ minus the sum, I goes from 1 to K, inner product of WI with itself over the length of WI squared, inner product of WI and WJ. But this is 0 for I different from J. So the only time this is non-zero is when I equals J. So this is the inner product of W prime and WJ. I only have to take the term when I is equal to J. I get WJ inner product with WJ over the length of WJ squared times the inner product of WJ with WJ. So this is WI, WJ. And the only time, sorry, this is WK plus 1, this is W prime. So WK plus 1, this is the new vector I'm defining, is my vector W prime minus the component of W prime in the direction of WI for all I from 1 to K. If I take the inner product of this with WJ, I get W prime minus, this is W prime here, inner product of W prime and WI over WI squared, WI. This is W prime inner product with WJ minus the sum, I going from 1 to K, W prime inner product with WI over the length of WI squared, WI inner product with WJ. This is 0 when I is different from J. So we only have to look at the term when I equals J. When I equals J, this is inner product of W prime with the vector WJ over the length of WJ squared, WJ inner product with itself, which is WJ squared. These cancel. So I get W prime inner product with WJ minus W prime inner product with WJ. That's 0. So that's what I wanted to prove. This vector WK plus 1 is perpendicular to every vector in my orthogonal set. So we now have the tool we need to describe what is called the Gram-Schmidt orthonormalization algorithm, or process or method, whatever word you prefer to use. So the problem is, what we want to solve is given the basis V1 up to Vn for a vector space V, construct an orthonormal basis W1 up to Wn with the property that for all k going from 1 up to n, the sets V1 up to Vk and W1 up to Wk generate the same k-dimensional subspaces. So we've basically already done all the work. So let's start with V1. First, I'm going to construct an orthogonal set with this basis with this property. And let's say W1 just be equal to V1. So V1 and W1 generate the same one-dimensional subspace because they're the same vector. So let's go step by step. Suppose we have V1 up to Vk and W1 up to Wk, sets of vectors. These are orthogonal, and they generate, these two sets generate the same k-dimensional subspace. So here's a kind of picture. Here's V. Let's say Wk is the k-dimensional subspace generated by V1 up to Vk or by W1 up to Wk. That is, these were the k vectors that we started with. And we constructed k new vectors that are orthogonal and generate the same k-dimensional subspace. And Vk plus 1 is not in this subspace because it's linearly independent of these k vectors. So it's not in the subspace W1 up to Wk, but by the lemma we just proved, we get a vector Wk plus 1 such that the subspace generated by V1 up to Vk plus 1 is the same as the subspace generated by W1 up to Wk plus 1. And this set of vectors is orthogonal. Now, so that's the complete proof. The trouble with the complete proof is it's so short, it's hard to miss what's going on. So you really need to set aside some time, sit down with the book on page 283, and whatever you need to know that comes before, and study this process. But everyone, so if you ever have a course for which linear algebra is a prerequisite, everyone will assume, your teacher will assume, that you know what the Gram-Schmidt orthonormalization algorithm is. So let me try to work an example, or a couple of examples, so we can see what's going on. And I'm doing examples in the book, so you can follow in the book, or you can study. You can study at home. Let's just see how it goes. So suppose we're in the vector space R2.
What page is it on the book?
284. And we have a basis for R2 consisting of the vectors V1, which is the vector 2, 1, and V2 is the vector 1, 2. So 2, 1 is this vector, and 1, 2 is that vector. So I want to construct, first I want to construct an orthogonal basis from this. So step 1, construct an orthogonal basis. So I want to let W1 be equal to V1. And what is W2 going to be? It's going to be V2 minus the component of V2 in the direction of V1. So this is going to be minus the inner product of V1 and V2 divided by the length of V2 squared times V1. So I have V2, and it's going to be, so W2 is going to be V2 minus the component of V1 or W1, they're the same in this case. The component of W1 is the component of V2 in the direction of W1. So let me just write this more neatly. It's V2 minus the component of V2 in the direction of W1. So that's the inner product of V2 with W1 over the length of W1 squared times W1. So what is that? V2 is the vector 1, 2 minus the inner product of V2 and W1, which is the same as V1. The inner product of V1 and V2, or V1 and W1, W1 and V2 is the same thing, is 1 times 2 plus 2 times 1 divided by the length of W1 squared. The length of W1 squared is 2 squared plus 1 squared times the vector W1, 2, 1. So that's 1, 2 minus 4/5 times 2, 1, which is 1, 2 minus 8/5, 4/5. So this is the vector 1 minus 8/5. So there's a typo in the book. Should be minus 3/5. And 2 minus 4/5 is 10/5 minus 4/5 is 6/5. So that's W2. So I start with the basis B, which consists of the vectors 2, 1, and 1, 2. I get a new basis called V prime, which consists of the vectors 2, 1, and minus 3/5 minus 3/5 6/5. And you can check these are perpendicular, these vectors. And then I can, so this is an orthogonal basis. And to get an orthonormal basis, I divide each of these vectors by its length. This vector has length 1 over root 5. So I get 2 over root 5 1 over root 5. And the length of this vector is what is the length of this vector? The length squared is 9 over 25 plus 36 over 25, which is 45 over 25, which is 9 over 5. So the length is the square root of that, 3 over root 5. So if I multiply each coordinate by root 5 over 3, I get minus 1 over root 5, 2 over root 5. So this is my orthonormal basis. So you can check that each of these vectors has length 1. They're mutually perpendicular, and it satisfies all of our requirements. So let me just go through this again, because this is a basic calculation that you need to know. I start with the vectors 2, 1, and 1, 2. So I want to find an orthogonal basis. I want to construct an orthonormal basis from this. First, I construct an orthogonal basis where the vectors are perpendicular. These two vectors are not perpendicular. And then I divide each vector by its length to get an orthonormal basis. So my first vector, W1, I always pick to be the first vector, V1. I don't change that. And W2 will be the component of V2 in the direction of W1. So W2 minus the component of V2 in the direction of W1, that's the inner product of V2 and W1 divided by the length of W1 squared times W1. So the inner product of these two vectors is 2 plus 2 is 4. And the length of this vector is square root of 5. The length squared is 5. I get 4/5 times the vector 2, 1. I subtract, I get minus 3/5 6/5, which is perpendicular to this. And then I divide these two vectors by their length and I get the answer. Okay. Let me do one more calculation. Suppose I'm in R3 and I take the following non-standard basis. I have the basis consisting of 3 vectors. V1 is 0, 1, 1. V2 is 1, 0, 1. And V3 is 0, 1, 1. So these are three vectors in R3. 0, 1, 1 is in the YZ plane. 1, 0, 1 is in the X. Sorry. Yeah, this is the XZ plane. And this is the XY plane. And I have the vector. Oops. Let's see. Oh. V3 is 1, 1, 0. This is the vector V3 in the XY plane. This is the plane where the Z coordinate is 0. This is the plane where the X coordinate is 0. This is the plane where the Y coordinate is 0. So I have these three vectors in R3. So I want to construct first an orthogonal basis. So I let W1 be equal to V1, 0, 1, 1. I let W2 be V2 minus the component of V2 in the direction of W1. So that's V2 minus V2 W1 inner product over the length of W1 squared times W1. What is that? V2 is 1, 0, 1 minus something times the vector W1, which is 0, 1, 1. And what I'm subtracting is the inner product of V2 and W1. This inner product is 0 plus 0 plus 1 over the length of W1 squared. 1 plus 1 is 2. So I get 1 minus 0, 0 minus a half, 1 minus a half. This is my vector W2. W3 is going to be the vector V3 minus the component of V3 in the direction of W1 and minus the component of V3 in the direction of W2. So V3 is 1, 1, 0 minus the component of V3 in the direction of W1. That's something times W1. W1 is the vector 0, 1, 1. And the component of V3 in the direction of W1, that's the inner product of V3 and W1 over the length of W1 squared. The length of W1 squared is 2, and the inner product of V3 and W1 is 0, 1, 0 is 1. So I get 1, 1, 0 minus a half, 0, 1, 1. That's 1 minus a half minus a half. Oops, sorry. I mean, that's correct. This is, maybe I should. This is the component of V3 in the direction of W1. But I also need the component of V3 in the direction of W2. So that's going to be the inner product of V3 and W2 divided by the length of W2 squared times W2. This is W2, 1 minus a half. And the inner product of V3 and W2, I get 1 minus a half plus 0. that's a half, over the length of W2 squared, that's 1 plus a half squared plus a half squared times W2, 1 minus a half, a half. A half squared is a fourth, a half squared is a fourth. This is 1 plus a half. This is 1/2 over 3/2. This is 1/3 times 1 minus a half, a half. So that's equal to that's equal to what it is. It's equal to 1/3 minus a 1/6 plus a 1/6. So if I take W3 is V3, 110, minus the component of V3 in the direction of W1, minus 1 minus a half minus a half, minus the component of V3 in the direction of W2, which is minus 1/3 minus a 1/6, a 1/6, I get what do I get? Component of V3 in the direction of W1. This is, sorry, this is 0 minus a half minus a half. So I get 1 minus 1/3. So I apologize for the incomprehensibility of this, but it's all done carefully and legibly in the text. I get 2/3, 2/3 minus 2/3. So this is perpendicular. This is my W3. And this was W1. And if you check, W1 and W3 are perpendicular. If you look at W2, 1 minus a half, 1, a half of this. These are perpendicular. So I have constructed an orthogonal set of vectors, and you'll see all the details legibly and correctly done on page 285. And you see, then you divide by the length of each vector and you get the orthonormal basis. So it is worthwhile spending some time going through the examples in the text. That's maybe the most valuable thing to do. You go through the examples in the text where everything is correct and done, usually correct, except for maybe a typo, but everything is done clearly and understand it. And at this point, we've basically covered everything I'm supposed to or wanted to cover in linear algebra. We have one more class next Monday, and I will assign kind of some review problems on this, what we've done since the last exam, which are really only 2 topics, eigenvalues and eigenvectors for 2x2 matrices, and inner products, orthonormal bases, and a few other things in inner product spaces. So I will put together a review sheet with problems, and I will be going over them. There'll be a lot of problem sessions between now and the final. So as you're studying the material and have questions, I encourage you to log into a problem session and take advantage of them. Okay. Anything before we quit for the day? If not, see you either at a problem session this evening, tomorrow evening, Friday afternoon, or in class Monday morning. Bye all.